Hi, I hope everybody's having a good day today. I thought we would first talk about a couple of theorems that are quite important in calculus. So the first one is called Rolle's theorem. And that's named after a French mathematician by the last name of Rolle. And it was in 1691 that this theorem was first formulated. And knowing that Sir Isaac Newton and Gottfried Leibniz, not too long before that, had formulated the first ideas of calculus, it gives you some idea when this was done. So anyway, Rolle's theorem says if y equals f of x is a differentiable function and f of a equals f of b equals 0. And I should say a differentiable function on the interval from a to b. So that's the hypothesis, and the conclusion is then there exists a value x equals c between a and b such that f prime of c is equal to 0. So that's what the theorem states. So we have a function y equals f of x, and we know that f of a and f of b equal 0. And what the theorem is saying is there has to be some place in here, some c, where the derivative is going to be 0. Now, does it make some kind of sense? Well, if you started to draw a graph from A to B, is it possible to get there without having a derivative of 0 at some point? First intuition might say there's no way of getting from that point to the other point without having a derivative of 0. But let's see if we can prove it using some of the things that we've done quite recently. First of all, since f of x is a differentiable function, we've proven that all differentiable functions are continuous. So we know that it's continuous. And we've also proven the max-min theorem, which says that all continuous functions on a closed interval have both a maximum and a minimum value. So we have that situation here. So either the max and mins have to happen at both endpoints or not. So let's first assume that the max and mins happen at the endpoints. Well, if the maximum and the minimum are both equal to 0, that must mean that all the way between a and b, every function value is 0. So that means that the function itself is f of x equals 0, a horizontal line, which means not only is there one value of f prime of c equals 0, all the values of the derivatives would be 0. Now let's look at the other case. What if at least one of the max and mins didn't happen at an endpoint? Say it happened at some interior point. Well, we know absolute maximums happen and absolute minimums happen whenever the derivative is 0 or undefined. We've proven that that's the only place we have to go to look for them. if they're not at the endpoints. And we're right now assuming that they're not at the endpoints. So that means we've also shown that local maxes only happen when the derivative is 0 or undefined. And that's where this comes in, that this is a differentiable function. So we know there's no places where it's undefined, which means it must happen where it equals 0. So now we know that there's some place in there where the derivative must be 0, where that local maximum or local minimum is. So, in essence, that's using some of the things we've just learned very recently to prove Rolle's theorem. Now, it is important to know that it has to be differentiable to guarantee that, because otherwise you could have a function that did this. And there would be no place between here and here where the derivative is equal to 0. Now, Rolle's theorem turned out to be really important, but it was a little bit weak. So, soon after he came out with that theorem, a new theorem called the Mean Value Theorem was stated, and it's very similar. If you don't mind, I won't even rewrite this. I'll save you the time. It starts out exactly the same way. We're talking about a function y equals f of x that's a differentiable function from a to b. But this time, we're not going to insist that f of a and f of b equals 0. Then we're going to say there exists a value of c between a and b such that f prime of c, but now instead of saying it's 0, we're going to say f prime of c equals f of b minus f of a over b minus a. So what it is it's a stronger form of Rolle's theorem, because you see, if f of a and f of b were both equal to 0, this would equal 0. So Rolle's theorem is like a special case of this more general mean value theorem. And the mean value theorem is, as you'll see a little bit later on in the year, is a fundamental part of proving one of the most famous theorems in all mathematics. So, anyway, that's the mean value theorem. Now, to prove the mean value theorem doesn't really require a lot of calculus at this point. Rolle's theorem needed calculus in order to do the proof of it. The mean value theorem takes Rolle's theorem and uses some algebra to kind of readjust the axes. So I think what I'm going to do, instead of going through all that algebra, because my main focus here is on learning calculus, I'm going to show you what would happen. The mean value theorem says there's a point A and B, and let's look what f of b minus f of a over b minus a represents. This point right here is b f of b, and this point is a f of a. So when you go f of b minus f of a, you've got the rise, and b minus a is the run. So that expression over here just gives you the average rate of change of the function f from a to b. It's the slope of this dotted line right here. And all the mean value theorem is saying is that somewhere, maybe right there, f prime of c, the instantaneous rate of change is equal to the average rate of change. That's what the mean value theorem is saying, if you have a differentiable function. So, without actually proving it, if you think about just tilting your head a little bit to the side like this, and thinking of this as the x-axis, you can see, maybe I should have made this function instead of down here, made it up here, you can see that the mean value theorem is just Rolle's theorem. If you think of this as the x-axis, we're just saying that this slope is the same as this slope. And if this was the x-axis, it would be 0. Anyway. It makes me sleep better at night to know that somebody went through all the algebra. But I just know you have so much time. And the purpose of this course is to teach you more calculus. If you ever really want to see that algebraic proof, it's in almost any calculus textbook. What I'd rather do is give you an example where the mean value theorem is displayed. So, say you were going, you had a walk or some kind of movement where you were moving a certain, you had a position equation where you had the position s of t given in, say, meters, and time was, say, given in seconds. And you had the function that described this movement. S of t equals 100 plus 1/10 t squared. Where s is in meters and t is in seconds, this would give you the position. And say your trip was from 10 seconds to 60 seconds. So that was your domain of that trip. Now, if we wanted to look at an expression similar to this, we would say we have A would be 10 and B would be 60. And at 10, this would be 110. So you'd have 10 at 110 miles, and at 60, you'd be at 460, if I did that right. And somewhere in between that, you've got this position function. It goes something like that. It's a parabola. What the mean value theorem is saying is that somewhere in between here and here, sometime between 10 and 20, there's a place where s prime of t equals s of 60 minus s of 10 over 60 minus 10. Well, let's see if we can find what that would be. S prime of t, the derivative of this is 0 plus 2/10 or 1/5 t, the derivative of the position. And then if you take s of 60, we said that was 460 minus s of 10, which was 110. So we went 350 miles in 50 seconds, or on the average of 7. What this is, I'm hoping you see, this is the change in position over the change in time during that 50-second period. So that's the average rate of change of position with respect to time, or average velocity. And what this is the instantaneous rate of change. So that's the instantaneous velocity. And if you solve it, some fairly easy algebra, you get t equals 35. So on the 35th second, we're saying the instantaneous rate of change is equal to the average rate of change. So this isn't a proof of the mean value theorem, but it's an indication in this particular case that it does seem to work. Now, you can look at a lot of other cases other than just position and time. And really quickly, I could just change S to V, and now where this is the velocity of the trip, say in meters per second, the only difference is, say that was, instead of a position equation, a velocity equation, this would be just v prime of t, and the rate of change of velocity is acceleration. So what that is kind of showing is that somewhere in this 50-second time period, the average acceleration would equal the instantaneous acceleration. Just like we showed in the first example, that there was some time where the average velocity was equal to the instantaneous velocity. Okay, now, before I go to one more example, just to show you that it has to be differentiable, what if I had a case like this, where this was the position and this was the time, and instead of getting a nice parabola, say it looks something like this. Now, the instantaneous rate of change of this function is either going to be this negative number or this positive number. I think you can see there's no place in between here where the average rate of change is going to be equal to the instantaneous rate of change. There's no place where a slope along here is going to equal this slope, and the same thing over here. So for there really to be a guarantee for the mean value theorem to work, it does have to be a differentiable function. Okay, so that takes care of two important theorems that will show up throughout the year. Now, before we end the day, there's something that's not necessarily related to this, but is somewhat historical and around the same time. Sir Isaac Newton formulates this idea of calculus, and he says, I wonder what I can use it for. And he said, I've always wanted to know what the solution to that equation is. And he said, well, I think it's the same thing if I just took the function and found the zeros of that function, the roots of that function. So he said, if I could figure out how to do this, I might have a method always of figuring out how to figure out the roots or the zeros of a function. And he said, I wonder if my new calculus can do that. And this is around in the 1680s, so a little bit before Rolle's theorem. Well, what he did, he didn't want to just solve this one function, so he took a general function. Y equals f of x. But he said, well, that function isn't going to really have any zeros. So he said, that's not going to work so well. Even Newton didn't think of everything at first. So he said, let me make a function that's going to really have a zero. And I want to find out what that zero is. So he said, well, maybe I could just guess. So he guessed right here. And he didn't know if that was going to be the actual root and he thought he might have to make other guesses, so he called it, that point, x sub 0 for his first guess. And you can see he wasn't a very good guesser on this case, because the real root is over here. But what he did is he went up and he put x sub 0 into the function and got this point, x sub 0, f of x sub 0. But unfortunately, f of x sub 0 didn't turn out to be 0, so he knew that he didn't really find it. Well, this is when he brought in his calculus. He said, I wonder if I take this point and draw in a tangent line. So he drew in a tangent line, and he said, I bet that tangent line will bring me closer to my answer. Maybe exactly to my answer, he was hoping. But he called this point x sub 1. So he said, the first thing I have to do to find x sub 1 is find out what this tangent line is. So he said, I got a point, and I know my slope right here is going to be f prime of x sub 0. So I have a point and a slope. He wrote the equation. Y minus f of x sub 0 equals the slope f prime of x sub 0 times x minus x sub 0. That was the tangent line. And then he knew that this point had to be on the tangent line. And the point was x sub 1 comma 0. So he put 0 in for y, and in for x, he put x sub 1. And then he just did a little bit of algebra to solve for x sub 1. So the first thing he did is divide both sides by f prime of x 0. That got rid of that. And then he just brought the x sub 0 over to the other side. And he ended up with x1 equals x0 minus f of x0 over f prime of x0. But when he found out that that didn't give him quite the right answer, he said, I just have to repeat it again. So he went up, plugged it in, found out it really wasn't the right answer, took another tangent line, and he called this new point, this was x sub 1, he called it x sub 2, and he realized that he kept getting closer and closer to the right answer. So he said, in general, I could put x sub 2 as x sub 1 and put x sub 1 here, but he came up with a general formula. He called this x sub n plus 1, and he called this x sub n. And then he had a formula. And this is called a recursive formula, because once you start out at x sub with n equal to 0, you can find out what x sub 1 is. And then once you find out x sub 1, you can find out x sub 2. Something that is called a recursive formula. And Newton called it Newton's method for approximating a root of a function. Now, once he did it, he wanted to try it out on his problem. So he has this, and he looked at this and said, oh, I bet you the answer is around 2. So his first guess was x sub 0 equal 2. But he put it into the function, and he found out that f of 2 was equal to 4. It wasn't equal to 0. He hadn't really guessed the right root. So then he used his new formula. He said x sub 1 equals x sub 0 minus f of x sub 0, which he found out to be 4. And then he realized, oh, I need the derivative. So he took the derivative of this formula. F prime of x is 2x plus 1. And he plugged in 2 to this and got 5. So his answer is 6/5. And then he said, that's not quite the right answer, so he did it again. So he took 6/5 minus, and then he plugged 6/5, so he took f of 6/5, and then he divided by f prime of 6/5, and found that that was a little harder calculation, and came out with 86 over 85. And calculations were getting hard, so he said, it looks like the answer is about 1. Now, if he only knew how to do factoring right up here, he could have just factored this into x minus, x plus 2, x minus 1, and he would have known that x equals 1 is a solution. So sometimes you can get a little bit too fancy, but what he had found was something that we still use now. I don't know, a lot of you probably have used graphing calculators to find a root of a function. That's how graphing calculators do it. They don't even know how to factor. Plus, if you get a really complicated function, this works out just as well as for simple functions. And that's why on a graphing calculator, they're going to ask you for a left bound and a right bound of your root, because this particular one has 2 roots in it, and they wouldn't know which one you were looking for unless you put that in. So anyway, Newton's method probably you won't use for the rest of this year, but it's such an interesting and historical thing, and the fact that it's still used on your graphing calculators to find roots, I thought you might be interested in it. So anyway, have a good rest of your day, and next time we're going to be talking about finding maxes and mins, really important things, and I think you'll like it.